Good morning, everyone, and welcome to this month's instance of the Spatial ML seminar series. And I guess today we have a very special talk from industry. We are like most of the talks in the past were from academic background, but today's talk is very special, and it's my pleasure to introduce Naif. Naif is currently a team lead and a staff software engineer at Tenstorrent. He got his PhD from the University of Toronto, and he was supervised by Professor Paul Chow. We overlapped during our grad school for quite some time, and I think a fun fact that Naif was my TA in one of the grad level courses that I took. So during his PhD, Naif was the lead architect for the Galapagos framework, which is an abstraction layer that basically allows you to implement applications on clusters of FPGAs and CPUs or heterogeneous computing devices, which is a common theme that he's working on at Tenstorrent. And today he's going to give us like an overview of the new generation of Tenstorrent architecture, the Blackhole, and also the software stack that goes on top of it. So thanks a lot, Nate, for making the time for this, and the floor is yours.
Yeah, thanks, Andrew, for the introduction. This is I'm a big fan of this talk series. This is my second time doing this talk series. Last time I did present the Galapagos infrastructure here, so it'll be interesting to do it from the industry side. So today's talk is it's this was originally presented by my boss Yasmina at Hot Chips. I'm gonna with some slight variations presented here today. So black hole, and I like to call it the stacks of software stacks because we have multiple stacks of software and there's synergy between these stacks. So I want to maybe touch up on that at the end. But main part of this presentation is to go over our hardware architecture and talk about one such programming model on top of it. All right, let's see here. Okay, cool. So it's just the agenda here. We're going to go over the architecture, briefly go through some roadmaps, then we're going to do a deep dive on the microarchitecture, talk a little bit about scale out, which is like a big problem that we want to solve here. And lastly, we're going to touch up on software. Throughout the talk, even during the microarchitecture part, I will talk about how the part of the software stack that I'm most familiar with would um, model on top of the hardware, but at the end we'll talk about how other software stacks could fit on top of that. All right, so where is my mouse? Okay, there it is. All right, so the AI silicon roadmap here. So we're gonna go back in time, 2021. We had our Grayscale processor, which is actually on this T-shirt too. I was just mentioning to Andrew that I have my black hole T-shirt in the wash, so I'd be wearing that instead. But yeah, so 2021, we had our Grayscale processor. You can think of this as your standalone PCIe card that you'd pop into your desktop machine like gaming GPU, right? Um, we had about 120 Tensix cores. I'll mention what a Tensix core is later in the presentation. Yeah, for now, bear with me here. We had 120 Tensix cores. It was on our 12 nanometer process, 100 gigabit per second LPDDR4. This was our starting PCIe connected card. So that was fine and dandy. But we realized that we need scalability, right? You have these models with a lot of weights. You want to try your best to keep it in SRAM, so you need more cards. And how are you going to connect more cards together? Well, that's where in 2022 we had Wormhole. So as you see, it's the same generation, so still 12 nanometer process, but the difference within this card is we're going to use some of the silicon on this card to pay for an Ethernet, right? So now we can connect multiple of these cards together. So we have maybe the accelerated portion of our AI application on a cluster of cards. and these cards can communicate over Ethernet. And that's that's a good continuation. However, for many reasons, such reasons maybe your programming stack isn't mature, you have to do some of your stuff on the CPU, or at some point you want to integrate it with another part of your application. You're going to get to the point where okay, the part that I chunked out for AI is amazing, but now the bottleneck is reading this stuff back in the CPU. So that's where today's or stuff comes into play, Blackhole, where we're looking at heterogeneity. Now we are in the land 140 Tensix cores. The other part of Blackhole is you may have noticed we went from 12 nanometer to 6 nanometer process. So we're getting even better compute acceleration there. But the thing that I want to highlight here with Blackhole is 2 points. Is our we've increased our Ethernet bandwidth here, so we have 10 by 400 gigabit per second Ethernet, as well as now we wanted to put the 16 beefy RISC-V cores. So I'll get into where all our RISC-V cores are. So, spoiler alert, like even within these 10.6 cores and the other cores that are mentioned here have tiny RISC-V cores for the control part of it. But now we have these beefy RISC-V cores that can run full-blown Linux, right? So with that part of your application where you want to go back to your CPU, you're doing it all on one chip. So that's kind of, how we came from 2021 to 2023 and, more. So this is from like a zoomed in photo of what black hole looks like. Like as I mentioned, we have these RISC-V CPU cores. We have 10.6 cores, and I'll get into the DRAM and Ethernet PCIe, DRAM and Ethernet cores later. But this is from a high level, this is what we see here. So we have our baby RISC cores. So these are RISC cores spread throughout all the other cores. And the baby RISCs are mostly for the control path of your application within your what I've denoted here as CPU cores. So your CPU cores are your big RISC cores, can run full-blown Linux, and baby RISC cores are running the control portion uh, of your application within these other cores that we have here. Other takeaways here, as I mentioned, we've increased our Ethernet 10 by 400 gigabits per second. And also the other thing to note is how are all these cores connected together? We have two NOCs and they're a 2D torus here. So, and we'll zoom in to what this looks like later in the presentation. All right. So yes, I've mentioned this. So on the right-hand side, we have our 16 big RISC-V cores. You can look at the specs yourself. A lot of cache, 3 levels of cache, 64-bit processor. Your baby RISC cores that are just your control path, you can see that the cache is a lot smaller, only 1 level, 4 kilobyte instruction, 8 kilobyte data. So it's very small. They're simply for control. And we'll see how they look like in their respective cores too. Okay, so this is what I've alluded to. We were going to now zoom in on some of the microarchitecture of what these cores look like here. So this is where your baby RISC cores are set up here. They're used for compute, data movement, and storage. This isn't exactly a one-to-one of, what's in your 10.6 because in your 10.6 you have both compute and data movement, but we'll see how all of that looks like in a second. But for now, uh, within a 10.6 core, which is one of the cores that I highlighted in that big grid, you have your hardened math engines. You have your tile math engine. I'll talk about what that is in a second. And you have your vector math engine. But tied to these hardened cores, you have your baby RISC-V cores that can be used to set up the control stuff needed for your hardened math units. Similar to data movement, we have we have hardened circuitry to talk to our NOC and our routers and other data movement portions like our DRAM controller and whatnot. Um, we have that as hardened circuitry, and we have our baby RISC-V cores to set up the control signals for it. And you would write you would write an application, a kernel on it by referring to a bunch of API calls to set up your control registers and set up uh, portions of your hardened circuit. And as you see here in data movement, Ethernet controller, very much the same. You have your baby RISC core that can set up your Ethernet controller with API calls. And lastly, storage. Again, very similar. You have your baby RISC core. It can communicate to DRAM core, your DRAM controller. So how does that look like in a Tensix core? So Tensix, this is our bread and butter for our AI applications here. And as I mentioned, it's Tensix Core isn't just compute, it's also data movement. So this you can tie what you saw in the last slide where we had RISC cores taught commu I guess paired up with different hardened bits. So here we have a RISC-V core, a baby RISC-V core paired up with some circuitry to talk to your router. Here we have another RISC-V core paired up with more circuitry to talk to your router. And we have, in our case, three RISC-V cores to talk to various parts of compute. And when you write an application, you could have, and this is like one such way to set up your application, you could have your compute kernel resting on these three parallel RISC-V, baby RISC-V cores that can do all the setup for your compute. And we'll get into what that compute looks like. I kind of alluded to it earlier. And we can also write our data movement kernels to communicate to these routers. So the uh, how we write these kernels, we have what we call lower level kernels. So these are, you can think of, if I was to, I could include a header that would have a bunch of these APIs that could handle reading and writing to the NOC, also uh, synchronization between different cores. The other nice thing about what we have for our API is, I guess, uh, whenever I talk to people about architecture, people are familiar with GPUs. GPUs has been taught for quite a while, very embarrassingly parallel. We have our application for a GPU where you have to, um, I guess, think about it with one program manipulating a bunch of different type of data. Here, in our architecture, you could have multiple kernels on different Tensix cores, so you can have multiple programs on multiple cores. You can also have the fine-grained control of reading and writing to any SRAM within the Tensix core. So for example, if I'm on Tensix core 00, I could say that send this bit of data to Tensix core 01, and then synchronize on this. And this is also a different kind of programming model. You could think of this as something like MPI even, right? Where you do sends and receives between cores. You can do that even within architecture. So this does open the door for a lot of different types of programming models here. And when you have some of these AI models that are fairly linear, but in different stages, you can think of how you could set that up. So yeah, I'm kind of alluding to how you might use this later, but yeah, from a high level, we have the capabilities to read and write to SRAM and DRAM, any SRAM and DRAM from any core, and we have synchronization primitives. So this is just a high level figure. Again, don't worry too much about the numbers here. I'm just throwing a bunch of numbers at you here. But the things to take away here is we have our 2D torus, both in vertical and horizontal, can go bidirectional at 83 gigabytes per second. And we have we have more bandwidth between the I/O as well, and even higher between SRAM to the NOx. But yeah, the main takeaway here, I would say, is how everything is connected with the 2D toruses in both directions. So this shows, again, what I was referring to in the previous slide, where because of um, these NOCs, you can read and write to any core from any core within your architecture. So this, I just want we're going to go through different examples of how data might be scattered within your application. So data patterns in matmls, comms, and sharded data layouts are pretty regular, and they map quite well to our mesh architecture. So first things first is if everything is local, right? Local or sharded. And I guess just to rewind a bit, when I say sharded, I'm referring to if you were to have, let's say, an application and you have it first, you have it in DRAM, and then you move it to um, you can think of this as a partitioned global address space, where once you split it out into this partitioned global address space, each core is now working on its local partition. And when between different operations, so let's say I do, multiple matmls in a row, I'm not moving that data. I'm only working on this local portion of the data. So I'm not spending any time or any bandwidth to move the data from my local L1, which is within each Tensix core, to some global space. But it's partition global because there is a mapping from my local partition space to this global space. So from a user's perspective, when I read and write to different parts of the tensor, it's actually reading and writing to the L1s underneath the hood. So I want to read and write, the first row of my tensor. That happens to be within the L1 of this Tensix core. And that mapping is kind of done automagically with our sharded infrastructure here. So it's just how the memory is laid out within our infrastructure. Anyway, so if you can, the takeaway here is if you can stay local, you're golden, right? Because then you're reducing traffic over the knock here. But let's say you can't do that. You have a conv and there's this overlapping halo region, right? You might see some of your bandwidth drop over here. Uh, let's say you needed to spread your compute even further, and you needed to do data movement across, a grid that we see at the bottom here, a multicast, or you wanted to spread across an entire column or row, you might see traffic drop a bit. Lastly, if the Tensix cores are a bit further and requires multiple hops, as expected, you're going to see some bandwidth drop. But the nice thing with our stuff is I think programming this is actually quite simple. And it's all possible at the kernel level for each core. So I've gone over a bit of the data movement portion of it now, just to step into some of the compute. So we have a tile math engine. Here, a tile we have defined as a 32 by 32 2D buffer space, and we can do a bunch of different operations on it. So matmls, dot products, element-wise transpose operations, and you would call operations to the math engine from these baby risk cores that are again in your control pad. So I would say, do a tiled matmul on this tile versus and this tile, and this would write the results to some sort of register where I could read back from in my baby risk core. So these are all that's kind of how this programming model works. So on top of tiled math engine, we also have a vector math engine. A vector math engine you can think of as a 1D array, which is popular for element-wise operations. We can also do sorting, reshuffles, and again, very similar to the tiled operations as before. You would include your lower level headers, and then you can call these as API calls. So this is where your user compute kernel would sit on these three baby RISC cores, and then they would interface with these math engines, or yeah, with these two math engines using these lower level libraries. Now, how do we put it all together? Well, I mentioned earlier that we have our data movement kernels that can read and write to anywhere on your chip. So let's say, I have a data movement. I want to read and write to the Ethernet core. I can do that. I want to read and write to my neighboring core. I can do that. I want to read and write to my core that's 3 hops away. I can do that. And then I can bring that data into what we call a circular buffer, which is an abstraction of our L1 memory. That from there, our compute kernel can ingest it, do whatever compute it needs to do. So then it'd say that, I want to do a map mul of the tile that I read from the core beside me. I'm going to bring it in. I'm going to do the map mul with something in my local L1, and I'm going to write it to this circular buffer where my uh, egress data movement kernel can ingest it and send it to where it needs to go. If that's the core next to me or Ethernet or DRAM, all of that is at the control of the user. So yeah, this is it's a similar programming model here. We have Tensix cores, we have DRAM cores. These DRAM cores are a little different, as expected. They don't have any compute. They have your baby RISC core. They still have local L1 memory as well as a crossbar to communicate to your DRAM controller at some point. Ethernet cores are similar. We have two baby RISC cores as well with uh, connected to routers so that they could read and write to the NOC. So, for example, you notice that it has two data movement cores because you can imagine that a lot of traffic is going to be sent to these Ethernet controllers that needs to go off chip. So, you know, speaking of off chip, here we have scale out. So this is, one example of how we could set all of this up. I guess a few things to take away is we can connect this in any topology that we want. We are looking at mesh topologies. We want to optimize for sharded data as much as possible, keeping data local as much as we can. But at some point, we still would need to go to different chips, and for that, we have these Ethernet cores. We can connect it in 2D and 3D toruses. In this figure here, we actually have a 3D torus where the green Ethernet cord is actually into the slides. So this is in the Z direction. And the nice thing about our stuff is you can lay this out in any way you want. And this is one example here. Here we've set up 32 chips in a 4x8 mesh, and we have it connected in the X, Y, and dimensions. So you can use these connections as you please. So lastly, I want to get into some of the software. I guess maybe just in case it hasn't come across, I'm actually on the software stack. So this is where I mainly work. The software stack that has been pushed the last little while, we call TT-Metalium. You can think of it as the CUDA analogous to NVIDIA GPUs, for example. And what I mean by that, and it's probably obvious from where I was talking about how you would write kernels, is if you want to write a good CUDA kernel, you have to know your hardware well. And if you want to write good Metallium kernels, you have to know your hardware well. You have to know this how your architecture looks like, where you want to grab your data from. If I want to grab it from my local L1 memory. If I want to write it to the core next to me, if I want to write it to Ethernet, if I want to write it to DRAM, I have to know all of that. All those kernels that I showed in the previous slides, those would be at the Metallium level of abstraction. So we have dedicated data movement and compute kernels. Um, and yeah, we the I've kind of alluded to this, but different cores can also run different kernels. So you can have data flowing through. So not um the application doesn't always have to be embarrassingly parallel. You can have multi-programs on laid out on top of our architecture. But is so it might seem like a lot, right? So there that lowest level of abstraction might not be for everyone, right? And we understand that. We have we this last couple years we've been pushing Metallium, but we've come to the understanding that there will be other experts at other levels of abstraction that want to um, get access to our hardware. And for them, we have our new TT-MLIR based compiler. The and on top of that, we have Forge, which TT Forge uh, is part of different frameworks where you can have like a pre-trained model in TensorFlow, PyTorch that would get compiled down to MLIR. And the nice thing that we have now is there's actually synergy between these stacks. So it's not three parallel stacks or even two parallel stacks. The MLIR work actually compiles down to the stuff that I was talking about at the Metallium level. So we have a bunch of these software stacks, and the nice thing is that they're all open source. Um, you can find us on you can find Tenstorrent on our GitHub, so github.com/tenstorrent, and then from there you'll find our other stacks that we have. So Metallium and TTNN is where I mainly work, but on top of us, we have these two new stacks that can hopefully integrate. They're quite new, and we're excited to see where that goes. And on that note, I want to thank you all for coming here.